So let's begin today's session. We are in 11th week. So first of all, I was thinking last class would be before time in this week only by Friday because in Monday I will be very busy next Monday. So let's see. I will request NPTEL team if they allow me. Then we'll have next session on coming Friday. Okay. So welcome everyone. My voice is audible, right? Time same time. Okay. So I think am I aud- I am audible. So let's see. As usual, we will recall first what has been done in the 11th week, and then we'll solve some simple questions based on the discussion. Okay. So let me share my screen
Is
first.
this your last class, sir?
No, no. There is a next session coming on maybe Friday or Monday, as it will be decided. And I was thinking to have one more extra class after 12th week. If you wish, I will have in next week. It will depend on my internet connection because I am going home in coming week.
ओके ओके थैंक यू सर कोई कोई बात नहीं सर
Okay. So let me share my screen first. Visible, right? It's visible, right? So let's begin. I think it is visible. So the week was started with definition, defining adjoint operator. Actually, it was defined in 10th week, but this week we started with recalling definition of adjoint operator, which is like this. If we have inner product space, let's say V, and T a linear operator on V, then T has adjoint provided there exists linear operator T star such that for any alpha beta in V, this condition holds. Okay. This definition was coming from representation theorem, if you remember last time. Representation theorem. In 10th week, we have discussed about this representation theorem. Basically, this special vector is completely depending on this beta. We get unique T star beta from where we have this definition. Okay. Mhm. So we have some properties of adjoint of let's say T and U be linear operator. Then relation between adjoints and actual T and U. So if you have T plus U, your operator T plus U, then adjoint of this operator is E star plus U star, okay, where star uh, is adjointness. Okay, E star is adjoint of. So this theorem was proved in the class. So I'm not going to prove, but I'm recalling these theorems because this will be important while solving exercises. Okay, so CT star is equal to C bar uh, into T. Okay, EU star is equal to U star. Okay, here we have reversal. Okay, For this, you might do like, okay, let me do few things. P U alpha beta. This can be written as u alpha as a vector. P will go other side, then it will become P star beta. Okay. Now u will go that side, so it will become alpha, and u star P star beta, and then this implies Pu star is equal to u star this P star. Okay. So this is how we prove third one. So similarly, this fourth is proved easily. Okay. Okay. So remember this adjoint of adjoint is again same. So we have next uh, isomorphism of inner product spaces. What is isomorphism of inner product spaces? If they are basically isomorphism first of all and preserves inner product. Okay. Preserves inner product means this. If you apply T, then calculate inner product, T alpha T beta. They are same as inner product of alpha beta. Okay. So this was definition for isomorphism of inner product spaces. So we have isomorphism of inner product spaces. We isomorphism of, okay, this is concrete definition. It is one and two linear transformation and preserves inner product space. Preserves inner product structure. Let's see theorems regarding this. That V and W be finite dimensional inner product spaces over the same field, say F, P be a linear transformation from V to W, then the following statements are equivalent. P preserves inner product, P is an isomorphism, P carries an orthonormal basis to orthonormal basis. Okay. Oh, here we have any, here we have some. Any guess. Anyway, if P preserves inner product, then any orthonormal basis will go to orthonormal basis. Okay. I mean, uh, norm one vector go to norm one vector. Like if we preserves in a product and let's say we norm b is equal to 1, then what will be norm of tv? This will be norm of tv square. Basically, we calculate if it is 1, then norm of tv will be 1. So this is tv in a product of p b with itself, but it is same as vv because t preserves in a product. But this is norm v square. But norm v is 1, so this is 1 square and 1. So basically, norm of tv is also 1. That is why unit vector goes to unit vectors. Just keep it just in a product. And orthonormal basis goes to orthonormal basis. This I'm leaving. This is also proved in the class. Just check once more if you don't feel comfortable into this. We have this corollary. Let V and W be two finite dimensional inner product spaces defined over the same field, say F. Then a linear transformation T from V into W will be an isomorphism if and only if their dimension is same. You understood this? If you assume isomorphism, then dimensions are same. This is obvious, right? Because the orthonormal basis will go to orthonormal basis. So dimensions are same. If dimensions are same, then this is morphism of inner product spaces. It is anyway 1 1. Okay. So because dimensions are same, it is onto also. That is why it become isomorphism. Okay. So let's see next. Next we defined is a professor defined a unitary operator. A linear operator T on an inner product space is called unitary operator if it is isomorphism from V to V itself. Okay. This is isomorphism. Okay, isomorphism of inner product space. So basically, unitary है तो this will preserve inner product structure. Okay, because isomorphism preserves inner product structure and sends unit vector to unit vector. So, let's see. Set of unitary operators forms an inner. Okay, sorry. Uh, the set of unitary operators on an inner product space makes a group with respect to binary operation as composition. Okay. So composition of unitary operator is again unitary. How you prove it? Just apply your definition. It preserves inner product space and okay. Basically, composition of isomorphisms is isomorphisms, and then you have to just check it preserves inner product structure. So if you have TU, okay, composition of U and T, TU alpha, TU beta. Now you want to check TU preserves inner product structure. Then this will become first because T preserves inner product structure, so it will be same as U alpha U beta. But U also preserves inner product, so this becomes inner product of alpha beta. So composition is also unitary, and because unitary operators are basically isomorphism from V to V itself, they are their inverse will exist. Once inverse exists, that will be also unitary. Okay, from the same line of arguments from this itself. P alpha P beta is equal to alpha beta. This will itself imply that T inverse alpha, T inverse beta, uh, basically if and only if okay, alpha beta. T inverse is also unitary operator, so uh, inverse exists. Composition is also in the also unitary operator. So all conditions are verified basically. Check if anything is missed. Okay. So this is set of unitary operators forms a. Let's say next theorem. This was for composition. Oh, sorry, associativity. No, no, no. We missed associativity. What is this? Closeness. First, first is that closed under composition. Composition is. Yeah, I'm leaving this. And this was for existence of inverse. So we have this next theorem on unitary operators. V be an inner product space over field say F. T be a linear operator on V. Then T is unitary operator. If and only if a joint of T exists and is equal to inverse of T. From this line, they mean T is unitary if and only if T star is equal to identity on V. Okay, and T star also like to T is same identity on V. So proof I'm not giving here. This is proved in the class. If you need to recall, You can watch, I think, third video of this week. Okay? Unitary matrices. What are unitary matrices? They're basically matrices which satisfy this similar condition. A star A is equal to identity. Okay. Same thing. From above theorem, B star T is equal to identity. Similar thing happens for matrices also. Same thing you can write here also. A star is equal to identity. Okay. How I'm writing it? Basically, they are simple. Use these relations, which in the first page, from maybe this third relation only. All these four relation will help solving these adjointness properties. Okay. Identity star is identity. Remember this. This is obvious, right? Your matrix, your first transpose I star will be, sorry, I transpose will be I only. Then taking conjugate is nothing, again I. So let's see next theorem. V be an inner dimensional inner product space. U be a linear operator on V. Then U is unitary. If and only if the matrix representation of U respect to some orthonormal basis, ordered orthonormal basis, it's unitary matrix. Okay. So there is one-to-one correspondence between unitary operators and unitary matrices. Okay. So this is what this theorem is. I'm leaving this also. Uh, okay. So next we have orthogonal matrix. An n-cross matrix over R or over C is orthogonal if and if they satisfy this condition. A transpose A is equal to identity. Okay. So here I think over R orthogonal and unitary are same, right? Because over R A transpose is same as A conjugate A star. So over R orthogonal and unitary are same, and over C they are different. Okay. So we have a theorem. I think this was last theorem, maybe not the last, but this is theorem in the last video. Let A be an n class n invertible complex matrix. Then there exists a unique lower triangular matrix M such that the entries of main diagonal is positive and M into A. Sorry, this is M into A. M into A is equal to U, which is unitary matrix. This is nothing but, if you see, coming from Graham-Smith orthogonalization. Okay. I will not. Orthogonalization process will do this. How? This is, I'm copying this because I think this is good to recall something. So this is proof maybe. Using Graham-Smith orthogonalization process, you get alpha 1, alpha 2, alpha n, which is orthogonal basis, okay, coming from some basis beta 1, beta 2, beta k, where alpha is calculated from this formula. Okay. First you calculate alpha 1 as equal to beta 1, and then if you calculate alpha 2, you can use alpha 1 in your formula. Okay. So this sum is up to k minus 1. So alpha k is coming from beta k's on this previous alpha k's which are already calculated. So this formula is for Graham-Smith orthogonalization process. So, but if you see alpha k is sum of linear sum of beta k and alpha is, right? But alpha k minus 1, that is also sum of beta k minus 1 and plus lower terms, alpha k minus 2 and so on. So if you replace all of them, your sum will be completely on beta k minus 1, beta k minus 2 and so on, beta 1. Okay. Alpha k can be written as linear combination of beta k's. Okay. And if you see here, if you write alpha k as a row, okay, alpha k as kth row, then this will be helpful in calculating matrix representation. The kth entry will be 1 because beta k is coefficient is 1. So diagonal entries are positive. This is from obvious things. Okay. So I'm leaving this, but we'll do an exercise on this. So basically, they are taking the unitary matrix as this. Okay. These orthogonal vectors which we got after Gram-Smith orthogonalization, we are putting them into matrix first, alpha 1, alpha 2, and in the each row to get so that norm of the row uh, means norm of any row vector becomes 1. That is necessary because we had a theorem which says a matrix is unitary if and only if all of its rows are orthogonal first of all and they are of norm 1 vector, norm 1 row vector like this. So making norm 1 vector, we are dividing by norm alpha 1, norm of alpha 2 and alpha 2 vector. So similarly, we get a matrix. Okay, this matrix is U, our unitary matrix. And these coefficients coming out of beta j, okay? Like this was ckj by alpha k while dividing. If you are dividing, you should divide both sides. Alpha k side by mod alpha k. Here also you are dividing everything. So you get this as mkj. Then this relation holds. Okay, and you got m also and u also. So we'll solve an exercise on this. Then this an exercise also solved in the class, but we have some question on this and we'll solve it. Okay. Okay. So next we have normal operator, which are basically such operators. They commute with their adjoints. Self-adjoint operators are these T star is equal to T, and they satisfy this condition, right? So they are normal. This and unit for unitary operator you have u is equal to identity. Okay. So unitary operator also satisfies this equality. U star u they are same. So they are normal. Unitary operators are normal operators. And then we have this last theorem. PV self-adjoint operator only. Then eigenvalues of T are real. Okay. Self-adjoint operators got real eigenvalues. And eigenvectors associated to different eigenvalue are orthogonal. So if you remember, similar theorem was uh, proved in fourth or fifth week. No, maybe sixth week. Something like eigenvalue associated to different eigenvalues. They are linearly independent, right? Here they are actually orthogonal. This is much more than orthogonal vectors are anyway linearly independent. Okay, so let's see. Now we are coming to exercises. So I suppose you understood them. We'll use them one by one if necessary. Okay, coming back. This is an exercise from the class. Okay, where this operator on vector space of polynomials on a polynomial function is differential operator. Okay, So we were wishing to calculate D star. What should be D star? Okay. When we calculate and what are the those conditions under which we can calculate. So first we wrote in this link D F D. This is defining relation on of D star. So we should get something like D star G, something like this for every FG in those polynomial space. So first we are calculating left side LHS. So this is star relation, and for time being, let's say G is equal to G star. Sorry, G is equal to G bar. Let's say we are in field, real field. Okay, to make it real so that no complication happens. So this inner product becomes just this bar came away, went away. So DFG is calculated like this. DF is equal to df by dx, and this is equal to this. But while calculating integration to 0 to 1, we get this value first minus of this. So this part is good. F in inner product of f with dg. So it seems like if this was 0, so minus d will be adjoint of minus d is good choice for d star. Okay, from here if you say. So but it should be 0 first. So if it is not 0, then we are suffering some. We want something like some constant f into some constant vector, maybe depending on g, some, let's say cg, something like this, so that you can take f common outside. So this becomes cg minus dg, something like this. So that this will be c minus d will be some operator which will be working as d star. But what happens in this relation? We have this relation, but this part, which I was leaving, saying 0, it is 0. F of 1 into g of 1 minus f0 into g0. This is a also linear functional, correct? Taking some f to uh, this constant value, which is maybe lying inside the field. So for phi, there is no vector. There is no vector. Okay, basically here we don't have g, so this is constant. This is constant. About what about this? F of 1 minus f of 0. Sorry, there is no h such that it satisfies this condition. This part also I did means I think we have done for integration. We don't have such kind of representation theorem, right? Right? Because if you see here, this is not finite dimensional, right? That is why we had this counter example, right? This was counter example where we said for every finite dimensional vector space we have such a representation theorem, right? And we get every linear functionality represented by some h. But this was counter example in the 9th week maybe. Yeah, 9th week. So this was a counter example. We have no such h to represent this phi function. Okay. So better it should be 0, because we cannot write this part into f into cg, something like f in a product with cg. So better it should be 0. But when it is 0, this star will exist if it is 0. So if it is 0, this implies this should be 0 for every f. So You can take f is equal to constantly 1 or minus 1, or f at 0, let's say 2, at 1, 3, something like different choices of f will give you different choices of f of 1, f of 0. So from here you conclude that g1 and 0, g0 are same, and this would be 0 to be this to be 0. Okay. So otherwise t does not have a joint. So here, if this holds, g0 equal to g1 equal to 0, okay, then d have a joint, and it is, if you see, f of minus d into g. Minus d is your that d star. Okay. So minus is coming, right? Okay, here we have minus. That is why I'm writing. So let's see. First question is on the same thing. That is why I was recalling this exercise, so that we can do this. Okay. I didn't write this, so I suppose we can do this together. So this is a space of polynomial in a product, a space of polynomial such that f of 0 is equal to f of 1. So if you see here, in this case, from this line, t star will exist provided this condition hold. Okay. So coming to our thing, we have f of 1 is equal to f of 0 for every f, right? Our vector space is defined like this, space of polynomials with this condition. So from here we have f of 1 is equal to, sorry, into g of 1 minus g of 0 is equal to 0 for every f in V. But for every f means we can take, for example, f is equal to constant polynomial 1. This implies g of 1 minus g of 0. Basically, they are same. G of 1 and g of 0, they are also same. Good. And this condition is satisfied. Okay. This is satisfied in our V. Okay. In question 1. So, so we have this, right? T and F are coming from our vector space only, right? There we have this condition. G1 and G0 are same. F1 and F0 are same. Any vector, take any H0, H1, they are same, because we have this our vector space satisfying this condition. Okay. So adjoint to exists. Okay. So second of, oh sorry, it said does not exist. This is incorrect. Adjoint exists. Now we have to check if it is self-adjoint, okay, or unitary. So for unitary, you should check u star is equal to, sorry, d star is equal to identity, and for self-adjoint you want to check d is equal to d star. Now if you remember this, in this condition, so first of all this is the explanation for d star exists. But if you see here, this part becomes 0 in this calculation. This part, which I was telling you. This is 0 in our case. So what left is this part. So this is nothing but we have, let me write here, d f g is equal to, first we get minus and then we have left with 1 f x d dg by dx dx. But this is nothing but minus of x. Uh, is I should write just f for clarity because I'm not writing f x here. Let me write here also. Minus of x in a product with dg by dx means just dg. So this is f minus dg. So you see here, this is your d star. D star is equal to minus d. This fourth option is correct from here. This fourth option is correct. Now what about C? Is this self-adjoint? No, because D star is minus D, not D. Okay, so what about first option? No, correct. What about first? Is this unitary? D into D star, this will become minus of D square. And this is, in fact, okay, this is not necessarily identity. Okay, why? This is this is never identity because if you check determinant of D square minus D square or eigenvalue maybe, this is positive, strictly positive maybe. Sorry, negative. My fault. Because determinant of D, if it is exist anyway, then it should be negative because D into D becomes determinant positive, and because of this minus thing, determinants become negative. So this is my fault. Let me write less than zero. If exists, I am saying. Or same applies for let's say eigenvalues. They have I has all eigenvalues positive and D minus D square has some eigenvalue maybe negative, right? Something like that. Or D square does not even have eigenvalue. Because this space is any infinity space. So determinant eigenvalue of this is not equal. Okay, this determinant and eigenvalue it does not matter. Okay, this part I'm leaving an exercise or check it. I will come back to this if okay. So first option is incorrect. Basically, which idea I was using, they applies only for n-dimensional vector spaces. Okay, it's determinants, but for eigen. Okay, so uh, this is obvious in some sense. I has every vector or I is an eigenvector, correct? Okay, this is obvious. Every vector uh, or I is an eigenvector with eigenvalue 1, value 1. Okay, I means identity operator. Don't confuse. But this is not true for minus d square. Okay, you can check for let's say x minus d square applies to x. what it will become? It will become 0, right? And this says x is an eigenvalue. X is, sorry, the x is eigenvector, e vector, eigenvector, and corresponding eigenvalue 0 with with eigenvalue 0. So here we have eigenvalue, all eigenvalues are just 1, and here we are getting some eigenvalue 0. So basically they are not same. So those operators are not same. So this is conclusion for A to be false. If you have doubt, you can ask, or I can go to next question.
Next question, sir.
Okay, okay, thank you. Which of the following properties are not satisfied by the adjoint of an operator in a finite dimensional complex in a particular case? Which is not satisfied. Okay. Such kind of questions are very we should take careful. We should be careful for that. This is correct option. So sorry. Let me write here. This is correct. This is incorrect because CT star will be T bar T star. Okay. This is incorrect because we just saw U star is equal to U star T star, right? And this is correct. So which options are correct? These options are correct. This is false. This is false. We are choosing in incorrect options. So, okay. So this follows from what we saw today. So let's see next question. This is this is just properties of headlines. We are leaving this. Necessary and sufficient condition that 2 cross 2 matrix ABCD is unitary matrix. Unitary matrix, for being unitary matrix, you should check A star is equal to identity or A star is equal to identity, whatever. A star should be identity. For this, let's write what is A, A, B, C, D. What is A star? That should become first column. Second row becomes second column. And then everywhere you should put bar because we are taking adjoint is equal to 1, 1, 0, 0. From here, you should you get first place norm A square, right? A bar becomes norm A square. Am I right? Plus norm B square. And in the second position, we get AC bar plus BT bar. And here we have A bar C plus B bar D. Here we have norm C square plus norm D square. So here we have 1, 1, 0, 0. Identity matrix. Now we should check, is first enough? First is not enough, right? First is not even talking about their conjugates. How can they satisfy? If matrix is real, okay, if matrix is real, so let's say C bar is equal to C. In that case, will they satisfy? Nowhere written that A square plus B square will become 1. So this is incorrect. That is not enough. Okay. But in the second, we have written now A square plus B square is equal to 1. So if they are real, now, sorry, mod A square is same as A square. But where and anything else? B is equal to minus C is equal to C. Then these two becomes 0 when our matrix is real. This is good. Oh, this condition is enough. This is enough, but for real matrices. This is right. This is enough. But this is sufficient only. No, no, sorry. This only one part is satisfied in this. Anyway, if this condition, all these conditions are satisfied, then our matrix will be. This is just sufficient. This is sufficient part. Sufficient for real matrices. But we are all talking about complex matrices and necessary and sufficient both conditions. So this is incorrect. Now, if you see here, okay, this is just one. This first place is done. This is for second one. This is also done. Now they are saying AC bar minus BD bar. This is 0. But this does not tells anything about AC plus BD bar. Okay, because here we have plus. So this is also incorrect. Only option left is C. Okay. So let's see what we get from C. Is C sufficient? Sufficient? Uh, A square plus norm A square plus norm B square is equal to 1. Let me say mod A square plus mod B square is equal to 1. So first place is done. We need C square plus D square is also 1, right? So C square plus D square. But C is, what is C? Minus B bar e power I theta mod square plus B is mod A bar E I theta square. Okay. But this is nothing but e power I theta got modulus 1. So this is nothing but mod B square. B bar and B both are basically of same modulus. So A bar and A also same mod. E power I theta is of mod 1. So this is, we are left with just mod A square. But A square B mod A square plus mod B square is 1. So this is also done, fourth place. Here I'm using this region, e power I theta is equal to 1 for every theta in real numbers. And I'm using this property also, a bar is equal to mod A for every A in complex numbers. What else? And this also, mod A into B is equal to mod A into mod B. So all these properties we are using, and then we are getting mod C square plus mod D square also 1. Okay. What left is we should show that these quantities are 0. I'm just showing for one. Uh, Similar thing will follow for second. So let's see A bar C plus B bar D. What is your A? A bar? A bar is not given, but C is given. Minus A bar, right as it is, minus B bar e power I theta plus b bar as it is, b is equal to a bar e power I theta. Oh, this sum is zero in, right? This is minus a bar b bar e power I theta. This is plus a bar b bar I theta e power I theta. So this is zero, right? Similar thing will follow for this entry, 1 2 entry. Okay. So this is zero. This is zero. Done. This is sufficient, right? And if it is necessary, this will also follow. But let me leave this as an exercise. You can just say like if there are four options for exam view point, if you already discarded your three options, the last option is anyway correct. Yes, let's see. Next question left as an exercise. Okay. So this was third question. If you help me in necessary part or do it by yourself. If it is done, very good. Okay, let me leave this part. Now we go to next fourth question. Okay, which of the following properties is R not satisfied by self-adjoint operator on a finite dimensional vector space, okay, in a product space? So for self-adjoint operator, you know eigenvalues are real, correct? So as a statement, it is correct. Eigenvectors corresponding to different eigenvalues are orthogonal. This is also just last theorem, if you remember this very last theorem. This part for self-adjoint operators, eigenvectors corresponding to different eigenvalues, they are orthogonal. Okay, so this is proved in the class. That's why I'm assuming and going ahead. So this statement is also correct because T is self-adjoint and it's a self-adjoint operators and orthonormal order basis to uh, orthonormal basis. Anyway, T preserves a norm. Is that correct? We have T for self-adjoint operator. We have T star is equal to T, right? So can we show that T preserves norm, or is it obvious for self-adjoint operator? What are self-adjoint operator? If this option should be incorrect. Okay, because we saw that unitary operators preserves norm, right? Okay, okay, let me write here. When T preserves norm, when let's say norm V is equal to TB, to T square both sides, then it is inner product with V itself, and this is inner product with TB itself, right? But this is saying that T is unitary, right? T preserves no, unitary operators are basically isomorphisms. T preserves inner product structure, then only you can say it preserves norm. So, but T star is equal to T does not even implies T preserves norm. T star is equal to T basically implies PV. sorry, TVW is equal to VTV, VTW, sorry, right. But this does not says that TP is a inner product. Okay, that is why this part is incorrect. Matrix representation for T over an orthonormal basis is Hermitian matrix. So if you over an orthonormal ordered basis, if you remember this the matrix representation of T uh, with respect to ordered orthonormal or orthogonal basis, what it comes, it just comes as matrix conjugate. As you take transpose and then conjugate it. So basically, the obvious relations between T and T star in the matrix representation holds good. So because T star is equal to T, what it says uh, now, one more thing to remember, because T star is equal to T, uh, corresponding matrix representation A star will be A, but this says A transpose. Sorry, this only says that A star is or or A is Hermitian, right? I'm right or not? What is Hermitian definition for Hermitian matrix? A star is equal to A, right? And when other definition, this is what T, and this is correct. If you have A star is equal to minus A, then A is said to be A is said to be skew Hermitian. Okay? So this definition is important in some sense, so that you should remember it. Otherwise, one day, let me share a little story while solving an exercise. No, well, while sitting on exam, I was looking for. This was my uh, very early age in my very early education. What is inverse means, and I was totally blank. So if you remember Hermitian matrices, then good. They are such matrices that A star is equal to A. And skew Hermitian matrices, A star is equal to minus A. Okay. So, but not satisfied. We were so this part is only correct option. Okay. So that is why I was saying be careful while solving such exercise. Okay. Let's see next question. I think you understood, right? All these options are basically properties
Yes,
of
sir.
self-adjoint operator. Good. Fifth question. We have invertible matrix. When there exists a unique lower triangular matrix M such that entries on the main diagonal of M are positive, and M into A becomes unitary matrix U. So what is matrix M? So if you remember, we should use Gram-Smith orthogonalization process for this, right? So let's see. This is not already unitary. I was thinking if it is already unitary, So take M is equal to identity and A is equal to U, but it is not unitary. You see, all rows are norm 1, but first and second row, they are not orthogonal. Otherwise, it should have been unitary matrix. Okay. Anyway, that was subconscious, subconscious mind. Let's see what is M here. So let's follow our orthogonalization process. Take a basis, which is beta 1 is equal to 1 by root 2, 1 by root 2, 0, beta 2 is equal to 0, 1, 0. Doing correctly. Let me see once more how it was done. So first we have beta 1. Let's see. Next question. Put last your vector beta 3 is equal to 0, 0, 1. Okay. Now, first alpha 1 we get is equal to beta 1 itself. So for second, alpha 2 is calculated from beta 2 minus beta 2 inner product with alpha 1 here and below. Norm alpha 1 is square, but norm alpha 1 is square is 1, so you can leave after some time. But let's write here 0, 1, 0 or beta 2 and minus beta 2 inner product with alpha 1. But it will be just 1, right? What is beta 1 or alpha 1? 1 by root 2. Sorry, 1 by root 2. It will become 1 by. Obvious inner product I'm taking. Uh, oh, this is okay. This is operator invertible matrix on R3 as a operator on R3, and we are just taking standard inner product space, okay, as a so that this inner product of beta 2 with alpha 1 becomes 1 by root 2. Normal alpha 1 is square is anyway 1 because normal alpha is 1. So we have alpha 1. This is nothing but 1 by root 2, 1 by root 2, comma 0. Okay. Now this is your 0, 1, 0, and here we have 1 by 2 minus sorry 1 by 2, 0, and it becomes minus 1 by 2, and here we have plus 1 by 2 and then 0. So you get your alpha 2. Okay. Now for alpha 3, how to calculate alpha 3? Alpha 3 is just calculated from beta 3 minus beta 3 in the direction of alpha 1, sorry, inner product alpha 1 by normal alpha 1 square minus beta 3 in the direction of alpha 2 projection I'm taking by norm alpha 2 square. What is this? We got what we are getting here. Let me write clearly. Beta 3 is 0, 0, 1, right? Yeah, 0, 0, 1. And then minus beta 3 in the direction of alpha 1. It is 0, correct? Beta 3 is 0, 0, 1, and alpha 1 is uh, third coordinate is 0 for alpha 1. So this completely 0. Check it. It- Okay. Uh, Okay. Let's see third entry of this sum. Beta 3 in direction of alpha 2. Now this is your alpha 2. Okay. And beta 3 is 0, 0, 1. So alpha 2 is also 0 in third coordinate. So when you take in- inner product, they are 0, right? Or I am right? Anyway, beta 3 is in third coordinate is 1 and alpha 2 in third coordinate is 0. Otherwise, so corresponding product, if you take coordinate wise product, everything becomes 0. So this is your 0, 0, 1 only. So now see, alpha 3 is just beta 3, right? The last column will be 0, 0, 1. So every matrix has last column 0, 0, 1. Good. So now what is your U? U is alpha 1 by norm alpha 1. This is your first bit row. Second row is alpha 2 by norm alpha 2. Third is alpha 3 by. So which option is correct for
Alpha 2 is minus 1 by 2, 1 by 2, 0.
alpha 2 is minus 1 by 2, 1 by 2, 0. But while
Normal.
when we divide by norm alpha 2,
Uh, 1 by 4 plus 1 by 4.
oh, sorry.
1 by 2.
Correct. Here this is minus 1 equal to this minus 1 only. Minus 1 by root 2. Comma 1 by root 2, comma 0. This is first entry. Means this is what it is written. Alpha 2 by norm alpha 2. Okay. So anyway, this is good. Or then we get here. Still there is little mistake. How we are getting 1 here? It's 0, right? 1 by root 2, 1 by root 2, then 0. Alpha 1 is like that. Beta. Correct. So which option is correct? I think B. B, right. We are getting minus 1. Okay. So this is from fifth question. Everything else is incorrect. Now, if you want to calculate M, you can just calculate like someone was suggesting UA inverse. But we'll follow procedure which is given in the classroom. We'll simply calculate it. We'll look what it is from here. I copied some related question from the class. To write, here it is. To write M, we should use this. This is lower triangular matrix or upper triangular. When Kj equal to this. When J is bigger, we are getting 0. So I think this is lower triangular matrix.
Lower triangular matrix.
Yes, lower triangular matrix. So what are diagonal entries? Diagonal entries are basically 1 by norm alpha k. So Let's see. I'm just calculating from classroom exercise. This is normal for 1 is 1, normal for 3 is 1, normal for 2 is 1 by 2. This is coming as 1 by root 2. Normal for 2 is 1 by root 2, right? So here in second position, we should get 1 by root 2. And every upper entry is 0. Now left is 3 entries. This question again, if time permits. Let T1 and T2 be any two self-adjoint operators on finite dimensional inner space P for complex plane, complex field. Let it start denoted joint corresponding operator when which of the following are correct. Is this self-adjoint? So it means, am I audible?
Yes, sir.
Okay. So this is not self-adjoint. If you say, take for example, B is equal to 0, A is equal to I, that is not self-adjoint, right? I of T1 star, this will be I bar T1 star, but T1 star is just T1, so I star, sorry, I bar is minus I T star. We are not getting just I T1, right? Oh, sorry, it is just T1. So this is not self-adjoint. This is incorrect. What about T plus I T1 plus I T2? They are asking it is normal or not. Let's check. Okay. To check normal, what we do, we should check A star equal to identity. One part is enough. Okay. Either A star is identity or A star A is identity. It's good enough because I star is identity. So let's see. T1 plus I is also IT2 star. T1 plus IT2. What it will be? T1 star is okay. Star is distributive. Okay. Now IT2 star, but IT2 star is, let me write it. IT2 star product with T1 plus IT2. Now what it is? Plus T1 star is because T1 T2 are self-adjoint, so T1 star is just T1. But uh, this will become, let me write directly, minus I. Okay. This is nothing but I bar T2 star. T2 star is T2, but I bar is minus I. That is why I'm writing minus I T2. T1 plus IT2. Uh, Now, if you use this relation T1 and T2 commutes, then this will be T1 square minus T2 square, right? No, minus I square will become plus 1. T1 plus T2 square. Oh, this is for unitary. My fault. Normal. Someone can correct me if I'm doing wrong definition. Normal is A star is equal to A star. Okay. So now let's see for T1 plus I T2, and here how it happened. You just cancel I T1 T2 I T2 T1 because of this relation. T1 plus I T2 star, this will become T1 plus I T2 of by similar thing T1 minus I T2. Oh, same thing. This is same. Okay. Expand this, we'll get it. T1 square plus T2 square plus I T, T1 T2 minus I T, T2 T1. Now, but T1 T2 commutes, so T2 T1 will become T1 T2 and this will become 0. That is why only thing is left is this. So this is normal. Nice. Now, about third, we have to check if it is normal. Again, it is now easy to calculate a similar thing. 1 minus I T2 star T1 minus I T2. It will become, first will become T1 minus T1 plus I T2. Because T1 T2 are self-adjoint. Are they self-adjoint or I am assuming T1 T2 any two self-adjoint operator on file? Okay, they are self-adjoint. And this condition is same, right? Because T1 is star is T1 only. So they are same condition in both. And this is nothing but T1 minus IT2. And again, this is T1 square plus T2 square. Similarly, on the other hand, this is also same as T1 minus IT2, 2 minus IT2 star minus IT2 star. Okay, so third is also correct. Good. So what about fourth? This condition is says nothing. If T1 and T2 is not commuting. So this is uh, basically problem is we cannot cancel these two terms. If T1 T2 is not equal to T2 T1, you cannot cancel them. That is why fourth option is fails and second, third. uh, Okay, good, understood. Okay, say, let's see next question. V is equal to T only, and it is understood as in a product space over real numbers equipped with in a product structure is alpha beta bar, the real part of alpha beta bar. Something like, let me write after. Okay, so after while solving this, I will write it explicitly. Then m gamma b multiplication by gamma for any complex number. So M gamma is self-adjoint for gamma belonging to real number. Let's see. M gamma. We want to calculate M gamma star is equal to M gamma. Question mark is this. A part. M gamma of alpha beta. This is this is nothing but gamma alpha beta because M gamma is multiplication by gamma. Uh, Here take gamma outside. So in the first coordinate, if you take constants, okay, now because gamma is in real number, it is working as constant. So we can take the first coordinate. Now send inside, but in the second coordinate, it will go becoming gamma bar, but gamma bar is gamma because it is real number. So conjugate will be itself. So this is just saying alpha m gamma because m gamma is multiplication by gamma beta. But this whole calculation from left to right here says that this is correct, right? M gamma bar star is m gamma only. Good. So let's see. Second, m gamma is self-adjoint for I into r, where I is square root of -1. We need for this above lines. Let's say gamma is equal to, we take I only. And I alpha beta same as अल्फा इधर जाएगा तो माइनस आई हो जाएगा, right? It will go and become I bar. First you take outside, it will be I, and then send in the second coordinate, it will be I bar. So that is why it will become minus I. These two are not same. This is M gamma is just Mi, and M gamma star is minus I. So this is not self-adjoint. You are getting uh, Mi is equal to M, sorry, Mi star is equal to M minus I, not the same. So this B option is incorrect. What about uh, C part? It says for every complex number, M gamma is self-adjoint. Is anyway correct, incorrect, or I it fails, or anything it fails. So this option is incorrect. But M gamma is unitary when modulus of gamma is 1. For this, we should calculate it explicitly. Let's see. Uh, M gamma is unitary. We want to prove gamma 1 to C. M gamma star is equal to identity. So let's say gamma, M gamma, alpha, beta is equal to gamma alpha beta, right? Is equal to, if it is in the first coordinate, gamma will go out. No. Am I assuming gamma as a constant? Yeah, I'm assuming gamma as a constant. Sorry. So gamma will uh, go out if it is in the first coordinate, as usual, for beta. So we'll use this relation, okay? M gamma alpha, comma M gamma beta. This is same as saying that from the first coordinate you get alpha gamma outside, from the second coordinate you will get gamma bar outside. It will become alpha beta. So this is nothing but norm gamma square alpha beta. But normal gamma square is just one because of this. This is just alpha beta. It preserves M gamma, preserves inner product. Correct? This line implies. And uh, so since gamma norm gamma is 1, gamma is non-zero, and multiplication by gamma and gamma is inverse. Sorry, invertible or isomorphism. Or say this all thing together implies M gamma is isomorphism of inner product space. Okay? Good. So nowhere I'm concrete, means nowhere I'm using this inner product structure. But while taking this gamma outside, gamma inside, this inner product matters. Okay, how can I say clearly that gamma goes outside? Because gamma is a complex number, right? So first of all, we should write m gamma explicitly and inner product is this explicitly. Let's say gamma is x plus iy, this fixed. Then m gamma applied to some random vector alpha plus I beta will be equal to usual multiplication alpha x minus beta y minus, sorry, plus I times beta x plus alpha y. Okay, this is your m gamma, which is defined explicitly. This is a linear transformation. Why I can say directly? Because alpha and beta are just having linear coordinates, or we are not just getting here alpha square. Okay? Something which is in linear polynomial, they're in they are actually, this is actually linear transformation of B. Okay? So this is linear transformation first of all. Is nice. It is invertible. You should check because uh, when gamma is non-zero, this then it is invertible. I'm leaving that part, invertible part. This is actually inner product spaces का isomorphism है. That is also uh, something to be checked here. Okay, so I'm leaving this. Be careful. Taking gamma outside the inner product. So you should look structure of this inner product. Okay, real part of alpha beta bar. Now the gamma is here. Let's say gamma alpha beta equal to, this will become real part of gamma alpha beta bar. Now here you should check that it satisfies or not. Uh, Not satisfying. My mistakes. If you take gamma outside, it will become complex number, and we want something real, right? So this way is not good, but the calculation in this way, from here, this is incorrect. After some time, it will become correct, but this step is incorrect. Okay. M gamma alpha, M gamma beta is equal to, and everything on one side. Let's say in the first quadrant or in the second. M gamma star alpha. Sorry, let me write it again. M. Sorry, let me write alpha here only. M gamma star here into M gamma into beta. Now it is your alpha, and this is M gamma star. Uh, this is your something multiplication by gamma into multiplication by gamma bar into beta. But now you get alpha norm gamma square beta. Now norm gamma beta square, norm gamma square will come outside because it is real. Okay, that is why this is just one, and you get alpha beta only in a product of alpha beta. It preserves in a, it is not directly coming outside. Okay, M gamma star is basically, M gamma star is a multiplication by gamma bar. Okay, you just check it. It is coming from this property. So this all thing, let me delete it. This also. Now it is correct. So here it will become gamma alpha and gamma beta. Basically gamma bar, gamma beta, and then gamma square will come outside, and then it is one and so on. So forth. Okay, so when, yeah, this relation holds when inner product of alpha beta is defined as real part of a alpha beta bar. Similar thing holds for trace, but anyway, this is for one dimension. That is why yeah, it works. Is there doubt in any line?
D is true, sir.
Is true? No, no.
D. Fourth option.
B is true? No, not true. See here, for gamma is equal to I, let's take gamma is equal to I, what we get, m gamma alpha beta means I alpha beta will be same as, I will go to second
Fourth,
coordinate and
fourth, fourth option.
what?
Fourth option. D.
D option.
Yes,
Yeah,
sir.
yeah, D is correct. Right. Because we saw below Uh, M gamma preserves inner product as well as uh, it is isomorphism. Okay, from C to C itself. Multiplication by some non-constant is isomorphism. You can check it by just saying that uh, multiplication by gamma. Okay, let me write it. M gamma inverse is basically M of gamma inverse. Okay, if you multiply by something, let's say some I, then multiply by I inverse, then that will be the inverse for initial operator. Okay, okay, good. Let's see next question. It is unitary. You know why? Because when nam gamma is one, then what is gamma inverse? This is nothing but gamma bar, right? Because nam gamma is basically you can write as a square, gamma into gamma bar. So gamma inverse is just gamma bar. So that is why unitary. Okay? In unitary thing, I can write it like this relation says m gamma star is nothing but m gamma inverse, and m gamma inverse is nothing but m of gamma inverse. Here, look into these relations. This will imply that m gamma star is just identity or one, one as a complex number, okay, or real number. Both one are same. Let's see next question. P be an inner product space, complex inner product space. P be self-adjoint linear operator. Which of following statement is incorrect? Okay, we should choose incorrect option. Let's see, verify first the option if it is correct or incorrect. Mhm. For every alpha, alpha plus it alpha same as alpha minus it alpha. Norm of them, essentially they are saying. How to check? Take square both side. Okay, both are positive number. Then this is alpha plus it alpha, alpha plus it alpha. Just look into this. It will become alpha alpha minus P alpha P alpha. Okay, this is from this minus is coming from I square, or it will become plus, right? From first coordinate we are getting plus I, from second we are getting minus I. It is plus I times alpha T alpha plus T alpha alpha. Yeah, T alpha alpha. Now what about second one? When we replace plus by minus I, so this we have same thing, but here No, no, there is a little mistake here in this calculation. Let me write it again. Uh, from here you have I T alpha plus alpha I T alpha. Okay. From here you will get sorry norm alpha square plus norm T alpha square plus I T alpha alpha minus I alpha T alpha. Okay. Now because T is self adjoint, right? This is this this is same as alpha T star alpha, but T star is same as this. So these two are cancelling out together. You get this part. If you don't understand, let me write it clearly. T alpha. This is same as alpha T star alpha. T star is again same as T, so this is alpha T alpha. So if you change correspond T can vary in first coordinate or second. So send it into second coordinate. Then this is plus I alpha T alpha, and this is minus I alpha T alpha. So they are cancelling out. Okay, good. So from this part you get this. What about this part? Alpha minus IT alpha. Alpha minus IT alpha. Similar thing will happen. Minus y minus I. Sorry, first coordinate is anyway. Sorry, first term is alpha alpha plus T alpha T alpha. Now in this part you should be careful. From the first coordinate you are getting minus I coming outside. Okay. From the second coordinate you are getting plus I coming out. So that is why it becomes plus 1 here in coefficient. And here you have minus I T alpha alpha minus alpha IT alpha. Again, T can go from first coordinate to second like this calculation. This is let's say star. So they will cancel out, okay? And you are getting norm alpha square plus norm T alpha square. So both are same from this and this. This option is correct. No doubt. Let's see part B. If T is self-adjoint operator, if you remember, all the eigenvalues are real, correct? Okay, so showing non-singular means just check kernel of I plus T, I plus IT, 0. Non-singular, 100 dimensional, na? I suppose this space complex, 100 dimensional in productive space. Non-singular is same as saying 1, 1. Okay, so if let's say P belongs to kernel of I plus IT, then I plus IT applied to V is equal to 0. This will imply that V plus I TV is equal to 0. This will imply that ITV is equal to minus V. This implies that TV is equal to IV, right? Now, it shows that T has an I is eigenvalue of t. Eigenvalue of eigenvalue of t. Okay, this is wrong because all eigenvalues are real because t is self-adjoint. This implies better v should be zero. Then only this condition is satisfied. So this calculation shows that v is equal to zero. Hence, kernel is trivial. Kernel of I plus it is just zero, and I plus it is non-singular. Right? So this is for part B. This is also correct as a statement is correct. Okay. Now what is written here? I plus I t alpha, I plus it beta imply if and only if alpha is equal to beta. But this is correct, right? Because I plus it is invertible. For example, your spaces. Assume that V is finite dimensional, okay? Then this is invertible. I plus it is invertible. Or send them both one side. Then I plus it to alpha minus beta is 0, right? These two parts are if and only. Now, because I plus it is invertible, so only thing which, or let's say non-singular, I'm using B, alpha minus beta is going to 0, it should be 0. This implies if and only if alpha should be, alpha minus beta should be 0, and hence alpha is equal to beta. So part C is correct. Oh, it's almost time. Sorry. Let me finish in 1 minute. And that's B as from B, similar to B. Calculation shows the I minus it is also non-singular. So this is incorrect. Now, main thing. The question is asking about is incorrect state. Okay. So what I wrote is all correct. Only part B is correct. Okay. So let's see next question and then we'll be done. 10th question. VB in a product space C3, AB matrix representation whose entries are like this. So basically A is this I power. This is 1 position, so this is 1 plus 1. This is I power 2 plus 1, I power 4, I power 4 here also, I power 3, I power 4, I power 5, I power 5 here, I power 6 here. This is your matrix, and this is minus 1, this is minus I, this is I power 4 is 1, so 1 is here, minus I is here. Here I power 4 is again 1 here, I power 5 is minus or plus I, here also plus I power 6 is again minus 1. Okay. Now they are asking about what is P star, matrix representation for P star. This will be nothing but A star. What is A star? Just take transpose and then conjugate it. Minus 1, minus I, 1, minus I, 1, I, 1, I, minus 1, base matrix, and then conjugate it. This will be minus 1, I, 1, 1, 1, minus I, minus 1. Okay, so this is good because standard ordered basis is orthonormal basis, right? 0, 1, 1, 0, 0, 0, 1, 0, 0, 0, 1. And under standard linear product, this is orthonormal basis. That is why calculating a trans a trans adjoint of is so easy. Mathematical. So let's see which option is correct. One I find out for me which option is correct. One in the anti-diagonal. So this is this is correct. Yeah. Okay. So this is end for today's class. Please calculate somewhere there is a mistake here. I left here to calculating while calculating this. Please calculate it. Do it. Okay.
Please upload today's stuff.
Yeah, yeah. I'll upload very soon.